Let's talk for a minute about the energetics of mixing. We may have noticed sometimes that when you mix two things together, the solution either becomes warmer or cooler. And these are examples of either exothermic mixing, where the solution becomes warmer, or endothermic mixing, where the solution becomes cooler. The reason we see this temperature change is because when we mix together two substances, there's 3 steps involved in this process. In the first step, first of all, we have to make room for whatever we're mixing together. So we have a solvent, and we have to separate those solvent particles. And when we do that, we have to break the intermolecular forces holding those solvent molecules apart. So that requires energy. So we see in this energy diagram, we have to move up because we're requiring some energy. Similarly, whatever we're putting in the solvent, our solute, we also have to separate. And again, we have to break those intermolecular forces to do so. Or if we have an ionic compound, we actually have to break those intramolecular ionic bonds. So that also requires energy. But then you put those two separated particles together, and now they can form new interactions, new intermolecular forces. And when two atoms or molecules come together and experience those interactions, that releases energy. So what we really need to worry about is the relative amount of energy required to separate our pieces, and then how much is released when we put them back together. If it costs less energy to move up than it releases when we go down, we can see overall we release a bunch of energy, and this is going to be exothermic. Didn't take much energy to separate our pieces, but it released a lot when we put them back together. On the other hand, if it takes a lot of energy to separate our pieces, but it only releases a little bit when we put them back together, this is going to be endothermic mixing. Overall, it required energy to do this. It took it out of the surroundings, and that's why it cools down. Now, sometimes we don't really experience an energy or a temperature change. This is what's called neutral mixing, and that would be if the amount required to separate them was pretty much exactly the same as how much was released. So if they start and end in the same place, that would be neutral mixing, and we also see that a lot. So we should be able to do some qualitative problem solving when it comes to the energetics of mixing. So let's look at the types of problems we could look at. When chloroform, CHCl3, dissolves in water, the solution becomes cooler. First question, really easy. Is the dissolution of chloroform endothermic or exothermic? Well, if it becomes cooler, that means it's going to be endothermic. If it's becoming cooler, it required energy to do this. It didn't release very much, and that was our endothermic process. Sketch a qualitative energy diagram. So anytime we're sketching an energy diagram, we're going to start like this, where on the y-axis we have energy, and on the x-axis we have time. And we don't have to draw the nice fancy one we had like on the previous slide. Anytime we just want a qualitative energy diagram, we can always start and just look and decide if it's endothermic or exothermic. And we're always going to put some energy in. And for an endothermic process, we just need to end at a higher energy than we started. So these would be my reactants and products, and we started at this lower energy, and this is the energy it required to break everything apart, and then it released a little bit of energy when we put them back together, and then it flattens out. And we can see here the difference between the reactants and products. This is my overall delta H. This is going to be positive in this case, which is consistent with an endothermic process. Last question, what bonds are broken in the mixing process and what bonds are formed? Well, the bonds we break are there's intermolecular forces within each of our solute and our solvent. So in chloroform, if we sketch our Lewis dot structure, looks like this. And then, of course, water. We know what He looks like. So when we separate these, we have to think about the intermolecular forces that would be holding the chloroform molecules together. So we just do what we've been doing before and decide what intermolecular forces it has. This is a polar molecule, so it has dispersion and dipole-dipole. But it does not have hydrogen bonding. It's got hydrogens, but it's not the HNOF. You remember the HNOF? That's when you have hydrogen bonding. So we can see that's not the case. For water, We look at this guy, everything has dispersion, of course, and then it's polar, so it's also got the dipole-dipole. However, it also has hydrogen bonding, so we got to include that too. So these are the bonds we break in the mixing process. We have to separate the chloroform molecules from each other, separate the water molecules from each other, so we have to break dispersion and dipole-dipole forces in the chloroform, and dispersion, dipole-dipole, and hydrogen bonding forces in the water. What bonds are formed? Now we have to think about the intermolecular forces between these two molecules. And so in that case, we look at the intermolecular forces and see what they have in common. And we can see the strongest one is dipole-dipole. So the bonds that are formed would be dispersion and dipole-dipole, but they're not really going to form that hydrogen bonding because chloroform does not have that, so we leave that guy off. That's why this would be an endothermic process. We see that we're breaking a really strong bond here, and we're forming a weaker bond. That's why we're not going to release as much energy. So we're going to break dispersion, dipole-dipole, and chloroform, break dispersion, dipole-dipole, and hydrogen bonding in water, and we're only going to form dispersion and dipole-dipole intermolecular forces once we mix them together.